switched back to like silicon computing. Actually, I saw like I would like to focus on silicon computing, like computing using the silicon, and the state of the art at that time product definitely was the CPU, right? I mean, in 2004, there was a great innovation and also competition in the CPU computing area. And the state-of-the-art technology on CPU, I mean, like a superscalar, like out-of-order processor, all this kind of great innovation and techniques I was able to learn those things in the classroom. When I went to the master graduate school, my advisor was Sean Lee, and he joined the school right after he worked for Pentium chips actually. So he taught us a lot of great techniques about CPU design, and I was very intrigued about those kind of computer architecture area. So I studied computer architecture, and I like to share this book, like the Pentium Chronicles. It's written by Robert Coel, who is a legendary architect who led this Pentium chip development from the beginning. And if you see the title of the book here, it's like the Pentium. The title is Pentium Chronicles. Um, I'm sorry. Let me go back to the. 어, 어, I'm sorry about this. My computer. 어,
현사님 그 슬라이드 쇼 탭으로 들어가셔서
예, 지금 하려고 하는데 잠깐만요. 컴퓨터가 어, 보기. 죄송합니다. 예, 슬라이드 쇼가
네,
줌
그쪽
인터페이스가 겹쳐가지고 예, 여기 있네요. 예, 죄송합니다. 예, 음, 죄송합니다. 예. So if you see the title of the book, the people and the passion, and it also mentioned the politics behind Intel's landmark chips. You see that if you like to do this kind of project, there are three kind of important things. We need the people, and we need the passionate people, right? And we need a quite here when you say about politics, it doesn't mean in a negative way, but we need some organization. We need some way to organize the people to build this kind of large scale chip. So this chronicle, I recommend this book. It's like how the project got started, how he built the team, and how he was able to build this kind of very sophisticated product at large scale, which also involves very like innovations as well. So so I read actually this book, and right after reading this book, I had a chance to join AMD as a kind of co-op student. In the US, there is when you do master, there's a program you can alternate between company and the school. So I almost spent during the master 2 years at AMD. And I was able to join the CPU design team in Boston and also Silicon Valley. And I had quite a hands-on experience on the CPU project that AMD team was doing at that time called the Bulldozer, which it didn't end up very good in commercial market. Uh, but um, but like all the kind of a theory and all these kind of organizational things that I read through book, I can see with my eyes like how really people are working there to build this kind of large scale. One of the, I think the largest scale kind of a semiconductor project at the time. So that kind of exposed me to not only to the technology itself, but also how we kind of organize the team, how we build a team to do this kind of very difficult product, actually. So, but in 2006, it's around the 2006, actually, if you are in graduate school, CPU was one of the, actually still the main computing platform. But you begin to see some like emergence of GPU computing at that time. So actually, if you know this guy, this is Ian Bug. He's still leading NVIDIA's computing platform. But his PhD thesis called String Computing on Graphics Hardware, which provided all the foundation for NVIDIA's CUDA technology, actually. So he is basically, the Ian Bug was the inventor, kind of is considered one of the inventor of CUDA. And noticeably, all his work was done as a graduate student. His PhD thesis was actually the foundation for CUDA. What I heard from the NVIDIA team, I mean, in retrospect, they say NVIDIA was never able to come inside NVIDIA, actually. Actually, that invention came from the school. And NVIDIA was able to, they were flexible enough and also courageous enough to observe that technology into their main product. But the invention itself actually came from outside, actually as a PhD student. So I think the graduate students and the PhD thesis, all this work, I think can quite have a huge impact on the steel industry. Because once you build the product, you become a little narrow scoped. It's hard to do like I mean very radical thing sometimes. So this is quite very inspirational work, I think, from Ian Bug. As you see, the CUDA, NVIDIA become the current NVIDIA because of the CUDA. But if you see their kind of if you read the thesis, I mean, you see that at that time the peak performance to talk about 60 gigaflops in 2005 2006. Now even our Renegade chip, our performance is 512 teraflops. So I mean, this computing capacity for the last 20 years has tremendously scaled, I mean, beyond our imagination. So this is kind of talking about the raw performance of a hardware, but here there is a very fundamental issue regarding the software they try to solve. So if you read this statement, mapping an algorithm to use primitive is not straightforward operation, even for the most advanced graphics developer. The results were difficult and often unmanageable programming approaches, hindering the overall adoption of a GPU as a mainstream computing device. So at that time, the GPU had all this rendering engine, and the main purpose of this programming model is to support the rendering, actually, the advanced graphic rendering. But they try to map other scientific algorithm, let's say this deep learning algorithm, let's say, or mining algorithm, whatever the kind of the algorithm other than this graphic rendering. But it's very hard to map those algorithms into your hardware. So they try to provide the better programming model so you can more easily map those algorithms so that it can make a GPU as a mainstream computing device. I mean, this become realized right now, right? I mean, GPU become truly the mainstream computing device because it provided actually the good programming, reasonably good programming interface to the developer. So when we approach the AI chips, you got to have two, in my opinion, we got to have two perspectives. One, we got to have a strong hardware, horsepower, all the peaks, everything. But it's very important, the very important layer of invention is this programming model, how you expose your hardware to the upper layer software and make this programming or optimization as easy as possible. So that's from the beginning, actually, when you started the Furiosa, to overcome the existing device, we got to really put effort into this programmability as well. So it was around 2006 and 2007, and after my graduate studies, actually, I joined the AMD's GPU team, and I didn't join the hardware division, but I kind of it was not fully my choice, but like I got more accepted into the software role. So I joined AMD's software division in Orlando. And I spent about 3.5 years as a software developer. At that time, more focusing on the developing the device driver for the rendering engine, actually. It exposed me so my background is more like I try to be more like hardware engineer, but I become software engineer. But it exposed me in the first place how difficult software development is actually, and the complexity of the software project. When I joined the software team, like I had this kind of the confidence myself, like I will master everything this driver, like in 6 months. But it turns out, even after all these 3 years learning about this driver, developing some parts of it, I realized I just knew a fraction of what's going on there, meaning that how complex, I mean, why we need such a huge team, I mean, how complex the software is on top of this hardware. Even like software is more complex than hardware. So they kind of, sometimes the hardware people underestimate the complexity of a software, but it kind of exposed me actually the difficult also software development should be at least as important as the hardware. So right after, so I spent about 3.5 years in AMD, and I came back to Korea. I joined the Samsung, and I joined the Samsung's storage team at the time. I spent also almost 3 years there, and I saw it was also a great experience to learn about the storage areas, like the memory technology and the storage technology. And but also I noticed the the organization is different actually. Let's say how AMD approached engineering, how Samsung approached engineering is kind of I see some difference. There's a pros and cons. Actually, the US team looks like a little more relaxed, but they try to really root cause all the issues. I mean, they are like they are more like fundamental. They take more, I would say, fundamental approach to the problem. Samsung, they are, but other compared to AMD, Samsung people are very quick. I mean, they are like super fast sometimes, and they are very their execution is sometimes it looks noticeably faster than the US counterpart. It turns out Samsung's SSD division actually become the world number one in the end. They did much better than Intel or other competitors in the market. So I think organization-wise, we like to combine both good things. So I mean, to win this kind of area, this kind of AI chip area, we need a strong foundation, basically. Without strong foundation, we cannot compete. But at the same time, like we also need to move very quickly. I think the strengths of, in some sense, I mean, sometimes we are very slow in innovation, but once we have innovation spirit, like our execution can move faster sometimes than our counterpart. So we try to have both strengths as a startup company. also as a startup, you should be move faster than the big company. But it doesn't mean like you should ignore the foundation. Once you don't have a foundation, I just said like you are not able to compete. So so we started around the 2017, and it has been 8 years so far. So first 3 years actually. So in 2017, when it started, it was very hard to get funding because from the very beginning, we targeted data center areas and infrastructure area. Please give me a minute. I'm sorry, but just give me a minute because I need to bring my battery charger. So please give me a minute. Sorry about that.
우리 백 대표가 아주 바빠요, 요즘.
너무 죄송합니다. 예.
예.
죄송합니다. 잘해. 이거 좀, 제가 없어요. 또 배터리가.
여기 보면 2017년, I met the Mr. Beck quite many times in 2017. I think it probably 2018. The time goes so fast.
Right. 이쪽 앉아 사세요. 그냥 이쪽으로 배터리가 아마 나갈 것 같아요. 예. 그 동전은 동전. 죄송합니다. 네, 렌트 이거 안 돼. 네, 일단 저쪽으로. 우리 저 원장님한테 안부지라. I'm so sorry again.
No problem.
So yeah. So we started 8 years ago, as Professor Cha shared. I was able to get a lot of good mentors about how we move forward. But one of the fundamental beliefs we had, even despite all these difficult challenges, is that the computing in the infrastructure at the data center level will be more and more important. So we decided to build quite a large scale kind of data center level chips that can involve both hardware, that's with silicon development, also quite a sophisticated software on top of it. I thought, so like in 2017, the first investor who invested in us was actually the Naver, actually. And at that time, Naver had a CTO called named Song Chang-yeon, CTO at the time, who is quite visionary about the technology. So they invested about like 500K. And there was another FI who matched the money, so we were able to raise about like $1.2 million as a seed money. But compared to our peers, global scale, I mean, like who also there was another startup emerging at the time. compared to other peer, we are quite underfunded actually, I would say. $1.2 million is not small money, but usually our peers from the start, usually they get funding around like, let's say, 30 million or 50 million, even like $100 million. But I think it turns out actually that the fact that we got kind of some more funding turns out to be a quite good thing for us in some sense. The reason is that because we got very underfunded for the first years, we are very able to focus on our fundamental architecture and the software and do all this prototyping, all these things in a very efficient way using, let's say, FPGA or some other platform. But for the first 3 years, we are not, and we are forced to not rush silicon development actually. So if you have like huge funding from the start, usually the team is rushing the silicon development. And once you start silicon development, you know, you need to spend the capital spending becomes quite your expense will really become huge when you launch the silicon development. But for us, like for the first 3 years, we were able to focus on our fundamental kind of aspect of this chip design. And also, 2017, in retrospect, was a very beginning phase of the AI. There was no transformer at that time. There was only CNN in 2017. And I think a transformer appeared in the late 2017, but it becomes more kind of mainstream in like 2019, 20. What I mean is that the AI workload we are targeting was changing so quickly, even nowadays, right? I mean, it's just changing. There is no kind of a slowdown of the progress of AI right now. And the progress of AI has a high kind of a relationship with the computing itself. You know, recently, let's say, like we talk about DeepSeek and like Llama, and we are talking about their innovation, like MOE, like a mixture of expert, let's say, of DeepSeek's MLA. If you think about those kind of architecture, it's all related to computing efficiency, right? I mean, all this innovation in model architecture turns out to be like, it's highly related to computing, meaning that it also has a huge kind of implication for our chip development as well. So if you spend too much money, rush develop your AI chips, looking at the workload at the state of art at the time, your chip becomes very obsolete when it comes out, when the new model comes up. So it's why also this flexibility, programmability, the chip that can accommodate the future change is also quite important approach actually. Because the silicon development silicon development takes at least 3 years, and it should cover the workload for the next 3 years. So when you start the project, you should foresee the workload for the next actually even like 5 or 6 years ahead actually. In AI field, it's almost impossible. That's also posing significant challenge to AI chip development. Even let's say big tech companies are developing their own chips. They need to foresee what they're gonna do for the next couple of years. But nobody is controlling their own AI workload these days, right? I mean, AI is the kind of the ecosystem innovation all over the world. DeepSeek can comes up. I mean, everything can come up. So the workload, what I mean, we should take it as a constant that workload will change. Then it has a huge implication for AI chip. You should try to achieve a much better efficiency in terms of energy than, let's say, GPU. But also it should be quite flexible enough to accommodate future change. That's I would say, the main challenges of AI chip. But I'm trying to emphasize we didn't rush the development, actually give us more room to watch what's going on and also work on the fundamentals. So the constraint sometimes is not always working bad. You can take it as a sometimes advantage as well, in my opinion. But for the after 3 years, we were able to get our Series A funding, which was around the $6 million, which was around 2019. And we were able to launch our first gen product called the Warboy. And that chip came out in 2021. And amazingly, I mean, I like to, that's the one thing that a little surprised some people around semiconductor. It was like one-shot silicon success, actually. Because when the usually silicon comes out, you know, sometimes you have to go through multiple revision to fix a bug and everything. But so a lot of people worried that as a startup, like we can screw up the once, even twice, then the company is gone. Like, you cannot recover as a startup. But we had a kind of one-shot silicon success. So one thing I like to say is the semiconductor is extreme precision engineering. So it doesn't allow major errors. Like software, you can fix the bug, but like silicon is extreme precision engineering, also given the very tight deadline. So your team needs high discipline and experience to make it happen, actually. And our hardware engineering team usually consists of the people who has a kind of strong background in more like the big company, let's say in Korea, Samsung, like let's say Hynix, also globally, let's say Qualcomm, all these kind of Intel. We were able to recruit this core group of our hardware people. And just one person in the team usually covers 10 person or 15 person in big company. As a startup company, we should also build some new methodology, how to automate, actually, not manual, how to automate, use the better tools. Let's say some existing hardware company use more like assembly level like language, then we try to adopt high level language, even though it's not super proven yet, methodology. So we try to be very aggressive in methodology. Also at the same time, we try to implement all the necessary discipline. So once the chip comes out, it's a very successful silicon because it doesn't give us any room for error, actually. So, but fortunately, our first gen chip came out quite successfully. It's not quite commercially successful because we use the kind of old, with a limited budget, you know, we use the kind of old technology. So the chip, to be honest, was like 2-3 generation behind compared to our competitors. But still, we were able to go through the entire cycle of the from the prototype up to the production. And we are also able to deploy this chip to some of our customers, actually, to apply this chip to certain services, even though it's a limited usage case. Then around 2021, we were able to finally get a little more like major funding, like $60 million. And we were able to launch kind of full-fledged kind of product development. And in 2021, we actually betted on LLM at the time. So as I mentioned, like we got to forecast the workload, what will be the important workload that will be used a lot. But in 2021, you see that all the GPT-3 paper came out in 2020 or 2021. When you read the paper, there was a very hype in the research community about this capability of those models. But still, nobody was sure yet. Those models will be practical model to be deployed as a service until the ChatGPT came out 2 years ago. It will remain as a research kind of project, or it will become the practical chip. But as an inference chip company, we betted on that workload. One of the main kind of the reason we betted on LLM at the time, we still believe that part is that we think that people like to use the most capable models. So the more capable model will generate more demand, even though it's a kind of expensive model. So there is no kind of a slowdown for the less capable. I mean, this is enough capable, so we don't need any more capable model. We don't see that way actually. So we like to pursue the more capable AI model. These days, people even think the AI models will become super intelligent, but we are pursuing that direction. And I think that model, that so-called frontier AI model, will be still the most important model that will generate all the demand. Because it's capable, we like to use the more capable model. So it's why we betted on this LLM model. The implication is huge in terms of chip development. If you like to target LLM model, you got to scale up your chip capacity, everything in computing, memory. I mean, in every kind of area, you got to scale up your chip capability to match, to run these LLM models. So our second gen development chip, compared to our first gen chip, we scaled up our performance almost 20, 30 times. So engineering wise, it's kind of also huge, huge kind of some people think it's a huge risk because we didn't do this kind of scale of a chip before, but we decided to go that way actually. So the Renegade Silicon project started in 2022, and after 2.5 years of quite very intense development inside, I mean, it was quite intense, I would say. The chip came out in 2024 May, actually. It's not noticed a lot by I think the community, but our second gen chip was also one-shot silicon success again. It came out and it's up and running. After 1 week, we got the silicon sample, and after 2 months of kind of optimization, we were able to demo the LLM, and we debuted this chip to multiple kind of more like well-known academic conference like HotChip, like ISCC. We published a paper, ISCA, Micro, and all this foundation innovation we were able to publish to the community. And there are some like community in the Silicon area who recognized our execution and the capability, all those things. And it's commercially, we shipped this chip to our early customer, like in Korea, like LG, Samsung, but globally, I cannot name the company yet, but we also are shipping and testing this chip with quite well-known global companies as well at the moment. So yeah, that's kind of the history up to the stage. But I'll say this is a quite beginning phase of our kind of a company, my belief, because we are just launching the viable product that has some product market fit. Our first chip is, I'll say, more like a POC level a product, and it's between POC and product. But our second gen chip, we believe, has quite a product market fit right now. It's targeting LLM. It shows good performance. It demonstrates some good efficiency as well. So we think we can penetrate into the market with our second gen chip, and we'll keep like a move ahead to bring out our third gen chip. We are already right now kind of in the exploring phase of our third gen chip. So we try to bring out our third gen chip in 2027. Still targeting the most frontier LLM models, but so there are many challenges ahead, I expect, and also risks definitely as a hardware company. But we are very excited about our opportunity at this moment. The reason is definitely from the beginning we targeted the inference at the infrastructure. I think the age of inference is here now. the first thing is the next scaling law is test time compute. Basically, it's a lot of inference compute, basically, right? So if you make the model think deeper, meaning that you do more and more inference to make the model like a region and to increase the capability of the AI models, meaning that there will be much more demand for this inference time compute. And also it has the more capable AI model means there will be more applications built on top of it. We are talking about agentic AI, all those kind of things. It can be a little hype, but like still the more capable AI model will generate more kind of AI applications that people are using, meaning that it needs more efficient inference computing, because the inference compute right now becomes the bottleneck in terms of cost. Even like OpenAI is losing money because of their all the infrastructure cost. I mean, a lot of company ultimately needs to turn profit, meaning that your infrastructure cost needs to be significantly needs to go down basically. And basically our AI chip value proposition is to make this AI computing more sustainable and economical actually. So I think this creates a huge opportunity for our product down the road. And also this open source AI, sometimes called like open weight AI, also is a good thing for the company like us because the workloads are more transparent right now. So you can, it's not like just specific to a certain company like Llama, DeepSeek, or like open source model gives very transparency to the hardware vendors such as us actually. So it's also good direction for the vendor like us as well. Let's say it's only proprietary model like OpenAI is doing, then we are fundamentally at disadvantage because we don't have access to them. But right now, all these commercial quality open source models also gives a very good playground for chip vendors like us. I'd like to emphasize that this is why efficiency is very important. And also, when you say about efficiency, it talks about the energy, actually. That's the most fundamental kind of metric we can talk about whether AI is efficient or not. And all our like hardware architecture innovation is about how we build better energy efficiency, achieving the same performance actually. So a lot of innovation on chip design is focusing on this efficiency. If you don't achieve this efficiency, there is no value of AI chip compared to, let's say, GPU, because it's still, compared to GPU, it has, I would say, less, its usability is still not that there yet. We are improving the usability and software, everything, trying to improve, but still the region our customer are looking for us is that even despite some difficulty, of using AI chip, they can achieve better efficiency, energy efficiency, leading to the better the cost structure. So here, the data center level, actually, if you see all the consumption of energy, up until 2019, the total energy consumption of a data center almost stayed the same due to all the efficiency innovation in semiconductor. But from the 2020, you see that the total energy consumption of data center increased very rapidly in 2003, but it even increased more exponentially, we predict, for the next 5 years. And the energy becomes actually the fundamental bottleneck to the AI. So we are also expecting, recently Sam Altman said that their GPUs are melting due to all the demand for their image generation application. It's just one single application makes the entire OpenAI infrastructure kind of almost like a full kind of capacity, their resource limit actually. Imagine that there will be much more inference demands for the next couple of years. Our infrastructure, I don't think is ready. If you think NVIDIA can solve all these issues, I don't think so. NVIDIA will remain strong, but their directions are not like super focused on this efficiency. They are actually trying to build even like a high performance kind of direction, or the mainframe, like data center scale. So what we can focus on, the way we differentiate is definitely we try to focus on this efficiency while satisfying the good enough performance actually. So when you talk to customer, let's say some like large scale AI inference customer, if you save 1 watt, it leads to $20 saving a year. So let's say your chip can save 100 watt. They can save $2,000 per year. And let's say they adopt like 100 of the chips for inference. It's kind of a huge capital saving actually. So they think it's very important that you save energy. It leads to the much cost-effective serving in the end. So our second gen chip, like we are very focused on enough performance, but also very efficient kind of AI chip. So it features 512 teraflops of performance and 1.5 terabyte per second of memory using the most advanced memory technology like HBM. But the more noticeable thing here is our target envelope is 150 watt TDP. So compared to our peer, who shows the same performance, they kind of show around the 250 or 300 watt. So we try to target this power range so that whoever services large-scale AI inference can adopt our solution in their existing data center without changing too much of the data center infrastructure. If you like to adopt, let's say, NVIDIA, let's say Blackwell, whoever, you fundamentally got to rebuild your data center from the scratch to accommodate all their technology, including like liquid cooling. Big tech company can do it, but like there are a lot of companies who try to still leverage their existing data center as much as possible. So our second gen chip, I mean, I think it's quite one of the largest scale semiconductor projects we did here in Korea. Also globally, it's also quite a large scale semiconductor chip. It packs almost 40 billion transistors. The die size is 653 millimeters square. You know, the NVIDIA Hopper is 850. So it's quite matches the scale of that, the NVIDIA GPU, and it's built on TSMC 5 nanometer node. It's using like 2.5D packaging and all this frontier semiconductor technology to enable this product. To enable this product, actually, like a lot of our engineering team, hardware team, who had like 20 years of this semiconductor experiences, they really, I mean, worked with all our global partners like TSMC, let's say on memory side, SK Hynix, all the kind of we collaborated together to enable this product, and we also accumulated a lot of kind of know-hows during that time through this project to enable this product. Actually, a lot of kind of know-hows to enable this product. I think that will be very valuable thing for our future product as well. So I think I almost spent 50 minutes already, but I'll just try to conclude kind of our kind of performance that we shared like actually last year. if you see the performance, like it almost matches the NVIDIA's high-end influencer chips, but it spends quite like significantly low power. And when running at that time, like the small LLM model, now the team is like really super focusing on this LLM and all this kind of frontier AI model to demonstrate the same efficiency and also quite showing the quite good performance. I think we'll be able to share quite good design win and also the competitive benchmark by the end of Q2 this year. And we are ramping up the production actually second half of this year. It's very critical period for us. Like we are generating the meaningful revenue out of this product starting like second half of this year and also next 2 years actually. And the hope like we need a lot of good engineers and customer support engineers right now. And also we need a really good, I realize, business execution as well. Hopefully, like some students here like to kind of, if you are interested in, just let us know, actually. We are looking for a very talented person all over the area at the moment. So how much like, can I do more like kind of this slide or?
Yeah, go ahead. Yeah,
Okay.
Okay. This is a very rare opportunity to listen to the founder and the architect of the technology.
Thank you. So I'll delve more into our technology, how we are differentiating there. From the beginning part, I mentioned about there is a hardware aspect. Also, there is a strong like kind of software part, and a lot of innovation happens between this hardware software interface. So what kind of like abstraction we need to provide actually? I think Professor Cha also like in-memory computing, all this database innovation highly related to also hardware capacity and everything. This like a holistic view on this kind of a system area product is quite important. And from the very beginning, actually a lot of our initial members, we had a chip architect, our co-founder. Actually, all of this innovation didn't come from me at all. All these things actually came from our CTO and our engineering team. A lot of this initial member were, some of them are software part. Actually, a lot of our talents came from the graduate the lab of the Seoul National University, the Software Foundation Lab, and all the kind of faculties provided great talent for us to initiate these things. And this AI chip design in 2017 was still in the beginning phase. If it's already mature phase, let's say, then it's very hard to compete, but still at the time was workload was still CNN level. So I think that also gives us some kind of confidence. Probably it's the right timing. We can accumulate all these kind of innovations as the industry evolves actually. But the main thing we try to do is this abstraction, how we provide hardware, so then to the software mapping problems as easy and tractable as possible. So we call our processor like a tensor contraction processor. Tensor contraction, by definition, is superset of matrix multiplication. So tensor contraction, by definition, is both I'll say multi-dimensional matrix multiplication. So why we a generalization of matrix multiplication? Why we emphasize this higher dimensional thing is that if you look at the hardware, it's more like natural. This hardware is more like 2-dimension. So the way even NVIDIA, the way the AI chips are developed is they put a lot of matrix multiplication primitives, whether it's a big unit or a smaller unit. All the AI chips are the same, actually. They put, because it needs a lot of compute, they put some matrix multiplication primitive, and they organize in some way, they interconnect each other and all of the things. And what the software does is, there is like a AI kind of the workload. They map this deep neural networks into this computing primitives. So basically, software's job is to map this to this mag unit as efficiently as possible. Actually, it turns out that this optimization problem turns out to be many NP-hard problem. It's quite large-scale optimization scheduling problem. And the issue is that this mapping is a very difficult problem. It sounds simple, but to build very competitive product, this mapping problem turns out to be very difficult problem. One of the fundamental issues is that this multi-dimensional, you got to map this multi-dimensional thing into this two-dimensional primitive. If it's a 3-dimensional thing, you map to 2-dimensional thing, a large scale, it's still, I'll say, kind of tractable problem. Let's say it's a 4th dimension. We have a hard time thinking about 4th dimension. Let's say 5th dimension, 6th dimension. But deep learning computing turns out to be, considering the usage case, it's 4th dimension, 5th dimension, 6th dimension kind of tensor construction computing. And it's why I would say there are like 10,000 engineers in NVIDIA who is still optimizing this problem into this mapping, who are trying to solve some of this mapping problem, actually. So if you do the same approach, we cannot compete, basically. So the way we do is we make our hardware primitive, increase the abstraction of our hardware primitive higher level, so that it can more natively process this higher dimensional matrix multiplication more natively at the abstraction level, so that this software mapping of everything is more tractable and it's easy. It's still a very difficult problem, but it's manageable and more automated than the manual approach the other companies are doing. So this kind of a paradigm, definitely we try to raise the level of the hardware-software interface. And this holistic view at the high level can streamline the hardware to maximize the parallelism and the data reuse. Data reuse is highly related to energy efficiency. So in the end, it can result in a higher performance and energy efficiency while providing some enough flexibilities to support all deep learning models. We have this paper at ISCA, and we will publish another kind of a short version, summary version in Micro. So I recommend to take a look at more details of all the details about our tensor construction processor. So I'll skip this part. Please let us know if you have any question about the paper. Please let us know. We'd like to kind of provide more detailed explanation to you. So this is the kind of how your hardware looks like in silicon. So yeah, I'll skip this part. It's about HBM engineering, and it's quite low-level silicon engineering, but what I'm saying is it covers many disciplines of engineering to build this the whole product, actually. And the software stack, if you look at our team, we have right now 120, 30 engineers now. And among them, 90 are software engineers. So we have way more software engineer than hardware engineers, right? And we can offload some part of hardware engineering to our vendors right now, but software the core part of software is all like in-house. Actually, it's hard to offload them because it's so related, intertwined with hardware. It requires at least like 1-2 years of our understanding our architecture for our compiler engineer to ramp up their development. So it's quite, the software is almost the integral part of this chip, we can say. At the high level, definitely we try to provide the high level API like PyTorch. We try to support PyTorch at the high level so that the user can run their model without changing their high level like environment. And we try to provide the backend to PyTorch, right? So if you write the code PyTorch, it can run through our stacks. And a lot of these things are, especially our compiler paradigm, the good part of it is not like a manual optimization. It's a global optimization approach. It's the only way we can compete against big company. If you do all the manual optimization like NVIDIA does, there's no way we can compete. So our hardware software enables that. We do all this kind of very NP-hard optimization, very difficult optimization in an automatic manner. That's how we can achieve the good performance and the better efficiency through this paradigm. So you can think of our approach as kind of a little different paradigm than the GPU approach actually. I'm not saying NVIDIA is not doing it. Definitely NVIDIA is doing all approaches actually. But their fundamental like kind of starting point are more optimized for their own direction, which is also turns out to be quite successful. But we are taking very different kind of paradigm of approach to compete here. We have a compiler engineer, almost 30 people in our team, who are had a fundamental study, graduate level studies, sometimes PhD, all those kind of who are very disciplined on this area, who are also very trained. We also have undergrad students as well, but I'm just saying very bright, smart kind of person, engineers who are solving one of the most difficult engineering issues right now. Actually, kind of excited about this problem solving. And software has a lot of parts. So we in the first hand we like to support PyTorch, but we also need to provide enough software so that the end user can deploy their models as seamlessly as possible. So we need to provide all this runtime kind of component as well. The most important thing for all the startups and not only startup big company, it's all about the team and how you organize it. What's your end goal, and what's your passion and what's your vision, what's your mission. All those things are quite important. And we worked on it for the last 8 years. And we are also very collaborating with also the schools as well. Because I mentioned the CUDA came from the school, basically. So these days, when you try to develop low-level interface, we try to work with quite a good graduate lab to kind of work on our programming model as well. So I like to emphasize this school startup and all this kind of collaboration is quite important part of this the innovation ecosystem. Thank you. Yeah.
Well, thank you. Despite your busy schedule, thank you for sparing your time, your precious time with us, and sharing your experience and sharing the core technology of Furiosa. I'd like to open the questions to the audience, but in the meantime, anyone can ask questions, and you can also ask a question in Korean if you like. But in the meantime, I'd like to mention one thing. You mentioned the Ian Bug's advisor. You know who's advisor? Who's his advisor? Not the Bill Daly, not Bill, you know, Bill Daly is not his advisor, actually, you know. Pat Hanlon is the computer graphics guy, you know, who got the Turing Award. And also he's a billionaire. You know, he also studied, he was involved in the company, and he also studied Tableau. You know, Tableau came out of the Stanford project. So, you know, now Tableau is part of Salesforce. But anyway, so, you know, he had a great advisor. And also the advisor was not just academic, but also has an entrepreneurial mind. So that's one thing that I want to say, but I have a question to you. Why did you refuse the acquisition of Meta? So I have my the guess. So, you know, if you get you know acquired by Meta, then you have to give up your product. In a way, you know, you have to integrate with the Meta's. You know, of course, you can use core part of your product, but you lose your identity. So that was my guess, but I just correct me if I'm wrong. You know.
Professor Cha, thanks for asking. And due to all this, I'll say everything, I'm not able to comment on
Okay,
the
I understand.
news
Yeah.
itself, but I can say the reason we are continuing our own path, definitely the identity kind of thing actually turns out to be quite important thing to us. But more importantly, we from the very start we just we see the opportunity is greater. We see greater opportunity, and we have also confidence about our product and the foundational technology. It's not there yet, perfect there yet, but I think we are in some sense, it's in the right direction. So that's
okay. I'm really proud. I mean, pleased and proud that you made such a big progress, you know, over the years. And because students are not asking questions, you know, I continue ask you know more. Let me finish one more question. So how much money do you want raise? How much money do you need for the next 2 years? That's what I mean. If I can help, you know, I'll be happy to help you.
At this stage, it's very true that we need capital to scale our product and business. So as also we are right now launching our third gen product. For our second gen product, total R&D we spent is around $100 million. But for our third gen, which needs more like a frontier technology, will require at least twice or 2.5 that our second gen R&D budget. So we think we need for the next 2 years around 300 million or a little above that range, actually. Yeah.
That's doable.
Okay. Yeah.
Okay.
Yeah.
Okay. Yeah. Now the next question from student Kim Sung-won.
Okay. First of all, you in the slides you mentioned that you compile down to an IR. Is this an in-house IR or is it something industry standard like SPIR-V or MLIR? I think it was yes.
So this
Yeah, sure.
Lord IR is our own IR actually. That's very tailored for our own like hardware architecture. But like there are multiple level of IR. Our higher IR level, we are thinking of adopting more like let's say ML IR or like open source kind of things in our plan. But like as you go lower, that the IR becomes more specific to your hardware.
Can I ask one more question?
Mhm.
Okay, so you said that you use page attention in KV cache block management. Do you do this via like virtual memory, where the hardware maps the address to the physical address, or is it like done in software, like as far as I know, the VLLM and etc. in the page attention, the address calculation is done in the code. So like this address translation, is it done by hardware or software?
It's the same way as VLLM does actually.
Okay, thank you.
Okay, thank you.
Any other questions? Park Hyun-min, yeah, go ahead. Can you show your face?
What? Yeah, can you hear me?
Yeah.
Yeah. Hi, thank you for the presentation. It was really eye-opening presentation for me. Other person already asked so many good questions related to technology, so I would like to ask you about the market situation when you started the Furiosa AI. When you founded Furiosa AI in 2017, the AI hardware market was already dominated by giants like NVIDIA or TSMC, for example. And what was your strategic vision at the time, and how did you approach entering such a competitive and resource-intensive market?
So one way we justified actually at the time, actually kind of I'll say I was justified, is that the market will be so big, even at the infrastructure, market will be so big. So there will be like let's say 1-2% of market we can penetrate. That will be quite good market for us. That was the kind of the way we kind of thought the risk actually as the market risk actually. The market will really go big actually. And another thing at the time, I think a lot of AI chip companies said the same thing. The GPU is more optimized for rendering still, and the GPU is not native for AI computing. So that was the another thing. So GPU still is not quite good product for AI computing. But for the last 8 years, it turns out NVIDIA still dominates the market, right? I mean, and it's hard to say it's any more rendering engine actually. NVIDIA chip is also very optimized for AI. Even its fundamental architecture is still like their CUDA based, all this GPU based kind of architecture, but so the some assumptions are a little naive at the time, I will say. But looking at now, actually, it's still it is still true that actually as an inference chip, it's finally become more realized there will be real inference demand at scale actually, because there was not many meaningful AI service for the first few years. There was some image classification, object detection, all those things, but you know those models are actually can process at the edge level and also CPU level. So at the data center level, it's hard to find a very meaningful workload. Though we expected it will come soon, but now you know these LLM frontier AI models are more like those models can run on the edge or robot. It's possible, but still we need a quite infrastructure, cloud computing to be able to run those models. So I think the opportunity is still very true. And the efficiency becomes more efficient. So it took a longer time to make this product quite competitive. It takes more time to make this more competitive. Yeah, but in the beginning, back to your questions. When he started, we had those reasons actually. Yeah, to justify our
Thank you
ventures.
so much.
Yeah.
Can I ask one more question?
Just one more.
You mentioned that it is important to wait a little while and observe how the market moves and predict the future rather than do something in a hurry. And I wonder if you have your own way or like your own know-how of making that conviction when targeting a certain area before deciding to develop a new technology.
I'm not saying it's our strategy. We are forced to do so. But sometimes I'm just trying to say. I mean, you gotta. It's always better to, move quicker and. But still, your constraint. I think startup is also always a constraint resource, right? Sometimes money or human, all those things. So you like to turn this constraint not to your disadvantage actually, but in the end you like to turn it into in some sense advantage. No, the other one is that startup definitely need to focus because you are constrained. You need to focus, right? I'm not saying you gotta move slower. I never intend to say so, but I'll say sometimes it takes time actually. So you got to be very tenacious. You got to move quick, but I'll say you need to adapt to the changing environment as quickly as possible as a startup. That's the advantage of a startup, right? So I said like for the first few years we were able to adapt to the change rather than we have some, because silicon kinds of is a fixed hardware. So once you make a certain assumption, like it's hard to change sometimes. But as a hardware vendor, I think if it's a hardware specific, I'll say hardware specific, like you don't want to rush too much, then you can be in trouble. Yeah.
It takes time to get the the startup in the scaling stage. So I think Furiosa is at the time of scaling. So that's why I asked you how much money you need for scaling. So maybe we can talk about later in privately. So I have there's one comment on the chat. Jonghyun Park. I think it's more or less a comment.
Okay, let me check. Comment. I'm sorry. I like check the.
이제 내가 읽을게요. 엔비디아가 성공할 수 있었던 부분은 칩보다는 CUDA 생태계였다고 봅니다. 그런 면에서 퓨리오사도 소프트웨어 생태계를 위해 노력하고 계신 것 같습니다. CUDA가 아닌 퓨리오사만의 인프런스 환경을 위한 소프트 생태계가 있다면 소개 부탁드리겠습니다.
So that's a very important part of our how we can build up our kind of ecosystem. So as our first strategy is we try to support a kind of high-level open source framework, but still our internal software are quite black box to our developer. It's hard to hack our hardware right now. So we only providing more like high-level API at the moment. But our next kind of a step is we try to open more like a low-level kind of interface that matches the kind of CUDA level. It's not gonna be same as a CUDA, but if you know the field, there is a Triton, which is a kind of high-level CUDA things. So we are working on it. It takes time, but I think we'll be able to share that more like low-level interface by the end of this year, and that can be trigger point for us to work more closely with developers actually.
질문이 많은데 딱 두 개만 받고 끝내겠어요. 그래서 please introduce yourself as a courtesy.
Okay.
김성원. Yeah.
So yes, I'm a freshman in 첨단 융합학부. And I would like to just ask one more question. So I think
Freshman means undergraduate work. Undergraduate?
I'm an undergraduate, yes.
Okay, good.
Yes.
Great.
So I think an important part of chip development is like I think you need to sell to enthusiasts as well as companies, because even though the companies may make all the revenue, if you like have the enthusiast share, then the people who are making these companies are like original enthusiasts. So in that vein, I'm wondering if you're going to actually, put your cars out to retail, if you have any plans for that.
Yeah, that's also a great suggestion. We are definitely considering that once we have those like low-level API, so that hardware or software hacker can work on, toy with our chips. I think that's a very important part. So yeah, we'll put our chips. We plan to put our chips on retail. We put our first gen chip on retail. Actually, you can find it in like Danawa and there actually. But we also will plan to put it. And surprisingly, there were some people who bought that chip actually on retail actually. But yeah, we'll put our chip on retail. We plan to put them on retail. Yeah, thank you for the suggestion. Yeah.
I can get it free to you.
Okay. Okay.
if you propose the proposal project.
Yes, absolutely.
The next Seung-jun.
I'm Seung-jun Chong, a PhD student. Thank you for your nice presentation. And I wanna ask is, can you share your goal of your next chip? I mean, it can be the improving the chip throughput. So as far as I know, your second generation chip achieves higher energy efficiency than the NVIDIA chips, but still the throughput is lower than the H100 or A100, or it can be the next goal can be improving the scalability, like NVLink in NVIDIA. So, and my question is can you share the next goal of your next chip?
Yeah, also that's very important questions. So in the first place, the Renegade performance is quite matches the A100 performance right now in terms of throughput. It's quite. We are still optimizing the performance, but it's quite competitive. The absolute performance itself, throughput itself, can be 800 performance with consuming way lower power and way more cost effective. So for your question, there are two parts actually. One is scale up. So how much you like to scale up as a single chip from second gen to third gen. We think memory capacity wise, so our first right now current chip is 48 gigabyte. Our second gen chip will feature at least like a 0.5 terabyte memory. So we'll have a huge memory based on HBM. And the compute performance wise, like these days we are talking about like FP4 and all these new numerics, but compute performance wise, it'll be also another like a 10 10x more performance than now. While we kept our power consumption reasonably lower than the NVIDIA actually. The way we also, so another part is scale out. So you mentioned about NVLink and all this interconnect technology. We definitely are, that's also very important part. So how much we like to scale out at the server level or rack scale level, but we are working on it. I cannot answer the exact scale of the, or how much we like to scale out, but it can be quite like a rack scale or like a multi-node actually, to cover all the goal, but the goal is that we like to run the most frontier AI models. We'll be able to cover the most frontier AI models with our solutions in an energy efficient way.
Okay.
These two, you have to set a priority among these two options. So which option is has the highest priority?
Scale up and scale out doesn't have to, it's not trade-off relationship. Actually, it's a scale up is like you just try to increase your single chip capacity. These days, TSMC and we try to leverage the most frontier technology like a chiplet. So you can put, let's say, multiple Renegade into single package actually. And use the better memory technology, but also the core invention we have, like our core architecture, we try to improve them. Scale out is how we interconnect all of them together, actually. Those things are not quite trade-off, actually.
I think it's already 10:27, so it's probably time to wrap up. Thank you very much, and for for sharing your passionate journey and your plan. I mean, I think I like to say that confirm that the Furiosa is an SNU startup.
Oh.
So in history, we want to leave it as a record. And the successful SNU startup, and I know at large scale.
Yeah, many of our workforce came from the graduate students or previous graduate students of SNU. But I also need to clearly mention that we have students from KAIST and other places there as well.
Yeah, but you basically started from SNU, so that's what I want to. Between the KAIST and SNU, so you have to say SNU first. Okay. Thank you. Yeah, I look forward to seeing you in person.
Yeah, sure.
Thank you.
Yeah. Looking forward to seeing you. Yeah, bye. Bye, everyone.
Bye-bye. Yeah.
Bye.